Hello everyone, I'm Zishen, a PhD student at Georgia Tech. And today I'm very glad to present our recent work on RRAM-ECC, improving reliability of RRAM-based computing memory. So here's the outline of my talk. So first, motivation and background. The computing memory is an exciting technique that can greatly increase the memory bandwidth and perform the MAC operations. It can enable the multiple word lines at the same time, making it as an excellent kernel for the matrix multiplication, which serve as the basis for the deep learning. And many non-volatile memories are actively under research for this computing memory due to their low power and high density, and RRAM is one of them. However, the computing memory faces challenges of device and cell variations. Like you can see here, the variation is increased because we have the multiple noise in cells, and the dynamic range is reduced because we have to encode the multiple states in the same voltage range. And what's worse, so the computing memory currently does not have a viable ECC scheme. So that is where this works come into play. So we propose the ECC scheme for this computing memory. And to enable this ECC for compute in memory, we make use of key observations. So based on the measurement data from our RRAM test chip, we really only see the -1 or +1 errors during this compute in memory. So if we take a look at this the confusion matrix, where the x-axis is the measured ADC output, and the y-axis is the expected ADC output, we can see that the errors will only occur in the -1 or +1 from their true result. And next, we will see how these observations can be used to enable the ECC for computing memory by walking through a simple example. So in this example, I will break down the ECC scheme into the 3 main components: encoding, detection and localization, and correction. And for bit data, we will use is showing here, and ADC results are showing below the array. So the first step is the encoding check bits for the performing the ECC. So the parity bits we encode here are exactly the same as the regular sectet. And the new encoding step is this 2 sign bit that serve as the checksum for computing the sign. So this is very important for the computing memory because we need to know whether the error is -1 +1. And the next step is the detection and localization. So as example, let us assume the single error occurs at the 3rd data bit. So instead of 3, we get 2. And to detect and localize this error, we can use the exact same logic as the regular sectet to localize the errors. And now that we have localized the error, the last step is the correction. So this requires to compute the sign of the error, and by comparing our expected checksum and its actual checksum. So here, for example, this lookup table implies is the -1 error, and then we'll go ahead to add 1 into this 3rd ADC output to complete this correction. And next, can we do even better? So we further propose a successive correction. So in this follow-up work, we figure out how to enable this triple error correction, and we made a use of two key ideas. So one is the less word lines can yield less errors, and second is we can detect 2 errors with the sectet. So can we use these detection capabilities to actually perform the correction? And that's an example on the right side. So what if we read 4 word lines and check for error, and if we find error, we will break down the 4 word lines into 2 sets of the 2 word lines. And if we get another error, we will break down the 2 word lines into 2 sets of 1 word lines. So this allows us to get double error correction. So how do we get the triple error correction? Well, a little known fact is that the sectet code we have been using can actually detect 3 errors because it has the Hamming distance of 4. So following the same logic as before, we can enable the triple error correction with triple error detection. And this can bring us up to the 10 to the power of the -12 bit error rate, which is competitive with the SRAM. And in terms of the implementation, we base on our RRAM array test chip, which is tape out in the TSMC 40nm technology. And what we add is 2 parts to enable the ECC. So first is this parity bit, and second is this decoder part to detect and correct errors. And okay, let's see some result. So for soft errors, we simulate a rest 18 with the different ECC scheme. And we find that is the DAC is double error correction and TAC is triple error correction can yield the lowest bit error rate for all these LRS variation cases. And at the 6% LRS variations, the TAC achieved the 4 orders of magnitude bit error rate reduction compared with the no ECC case. And to scale the ECC scheme to more parallel like word lines, we find that the TAC can enable the 32 word lines at lower bit error rate than 8 parallel word lines with no ECC. So that means the TAC ECC scheme can achieve the higher peak performance for a given bit error rate with the no ECC. And in terms of the overhead, we find that this additional logic for the ECC costs 16% more like area. And in terms of power, they cost 31% overhead over design without any ECC. And lastly, the summary. So the computing in memory faces challenges of the cell and device variations and post reliability issues. And we propose the ECC scheme for the computing memory, and it's like that, and it's a successive correction. So we achieved more than this 16,000 times improvement in the bit error rate over the no ECC, and can make the bit error rate of computing memory competitive with the SRAM. So with that, I will conclude this presentation. You're welcome to check our papers for details and contact us for any questions. Thank you for listening.